So the third item, I mentioned mere symmetry, just to use it. Now, all I want to say is how it looks to me that it will turn out. And then when I have time, or when someone else has time to show me what this will be. We've just had G, and we just had GL. And what we've seen is the Hecke eigenvalues here on GL are parametrized by connections, unitary or holomorphic, with values in GL. So that means basically we observe that those were basically semi-simple conjugacy classes. We make some restrictions. Semi-simple conjugacy classes in GL. So that's basically Cartan subgroups with an element of the Cartan subgroup in there. But so that's basically we pick some form of the maximal torus in GL, and it's basically a section of that, an algebraic section of that. But with GL, if we're working with in the geometric level, these groups are very, very close. At the arithmetic level, this is quite a different group. This is a group over a number field, or locally it's a group over R or C or a p-adic field. But when we're working with the geometric theory, this is a group, it's a complex group locally, and this is a complex group locally. So, or they're groups over the function field of X. And the tori are a little bit different, but basically the same. And my feeling is, and it may be completely wrong, I have to verify it, but mere symmetry has a great deal to do with the fact that these groups are almost the same. Almost the same. Now, but in the geometric theory, something entirely different, entirely new enters, and that's gauge theory. Yang, Mills equation. Now, all I want to say is here is that when you look, so in particular Maxwell's equations, I gather. So what we see is that here, this kind of duality, which is the mere symmetry, so that's somehow some kind of duality. That's what the word, if I'm right, it's duality to separate it, distinguish it from functoriality or reciprocity. And the new element is that one introduces the Maxwell's equation. So there are two possibilities, it seems to me. With this new element, from the point of view of differential equations, we're dealing with something which is very interesting mathematically, which is half of the possibility. The other, and that would be true independent of its physical interest. It would just be an interesting mathematical object. And the other possibility is that whatever one gets here is of interest physically. Now, one day walking home from work, I met a colleague in the School of Mathematics here at the School of Physics here at the Institute of Advanced Study, and I said to him, well, since this business is somehow seems to be included as part of the Langlands program, I want to know whether I should be embarrassed by it or not. Namely, is the physics of any interest physically? And he said, well, no, it can't be because the particles predicted or needed don't exist. So I would really like, just for my own information, to understand whether this view of things is true, and if this is not true, if it's something else, what is true, and whether the theory that is implicit here is a mathematically interesting theory, which I can well believe, or whether it's a physically interesting theory, and if my colleagues to be believed, and I'm inclined to believe them, this is not so. So that's all I want to say about 3, is that I think we as mathematicians need to understand this concept of mere symmetry, and we need to understand exactly what is mathematically interesting about it, and whether there is anything physically interesting about it. In my case, just to protect, so to speak, the integrity of what is referred to as Langlands program. Other people will have other reasons for wanting to know these things. So that's that. That's all I want to say about mere symmetry. It's just that's a relatively simple project. One just has to sit down, get out the necessary books, necessary papers, and study them until one understands them. Now let's come to reciprocity. So I want to say this is probably the most difficult of all. If we have functoriality, then I haven't described it, but it's relatively easy to associate to the theory of modern and what one might call automorphic Galois group. Sometimes the word Langlands group is used, but I don't know that I particularly like that. It doesn't have the necessary clarity. Now, Grothendieck had the idea that he could introduce in connection with algebraic geometry over the algebraic geometry over a number field, but also over C. He could introduce, so let's say here, a sort of motivic and in something else that's on my site called an appreciation, something I wrote on peculiar occasion. It is explained what has to be proven in order for this Motivic Galois group to exist. Existence demands some form of the Hodge theorem or the Lefschetz theorem. All right. So it's not obvious. Now, what is suggested to me, and I suggest it to you, to the audience, or to anyone who watches this video, for what it's worth, is that the thing to do is perhaps the following. I've suggested it in various papers over the years, but I haven't really had a chance to think about it. And once again, this may be a problem that's, so to speak, really over the level of my knowledge of mathematics and over the level of the strength and energy that I have to put into mathematics. It seems to me that the intelligent thing to do is to say, good, what does one expect from what should reciprocity be? Reciprocity should be the existence of so this is a group in some kind of Tanakian sense, but it's really, when all is said and done, can be thought of as a reductive algebraic group over C, Reciprocity should be a map like that. That means that whenever you have a motif, you have an automorphic representation. That's what you're trying to prove. So, but we don't have motifs. I said we might be able to prove functoriality with enough. Somebody might be able to do it, or several people might be able to do it over time. But what about M? M demands a theory of motifs. And this theory has escaped the algebraic geometers, even those who believe in it. Does it make sense to suggest that one should simultaneously prove simultaneously the existence of M? So this Tanakian group, the existence of M associated, prove simultaneously the existence of M and of the arrow A to M. I've been a little bit casual because one might want to consider motifs over C, one might want to consider motifs over a number field and so on, and it's somehow the motifs over a number field that belong in arrows like this, because A is defined with respect to a given number field, so M wants to be defined with respect to a given number field. But I suppose that study of general motifs can always be reduced to study of motifs over a number field. So this is all I want to suggest now. I think it would be, I've never really sat down and thought about it, but here it's a question too of informing oneself about what kind of deformations are allowed here, and just of examining all the literature associated with p-adic representations and so on, the kind of deformation theory that's implicit in the proof of Fermat's last theorem, and somehow overcome the widespread and as far as I can see, by no means justified pessimism connected with Grothendieck's idea. It isn't Grothendieck's pessimism, it's the pessimism of his students and his colleagues. So my inclination would be to try to develop a theory that worked, and to try to develop it by developing at the same time, or verifying and proving at the same time, the existence of such an arrow. So that's a much vaguer suggestion than the suggestion I make in the case of functoriality. Functoriality, I have a very strong feeling exactly what happened. Here I don't have a strong feeling as to what happened, what should happen, but just a feeling that maybe one should play around with these ideas. All right. Now, I've finished. I've said everything I wanted to say, but our cameraman has left the room and not returned. So let me just add a couple more words. So let me add that the fifth, I've said all I need to say about the 0.5, about the zeros, about the L functions. That this idea of studying the L functions as studying families of L functions and seeing what one can say about the zeros is at least an activity which promises to be rewarding, and one can hope that if one continues in that direction, some new idea about the Riemann hypothesis and so on might appear. But I don't think that one has the right to be too optimistic, but nonetheless, certainly it would be foolish not to pursue this notion of families of L functions. So now let me just tack something on about Frobenius and Hecke. And why I like the use of the word Frobenius, Hecke. Frobenius Hecke parameter. I wouldn't do this, as I said, but our cameraman has deserted us for someone else, other people. They're building there's a tent being constructed outside the Institute for the Physicists. So let me just say this. Frobenius Hecke, I think, have offered a great deal to the analytic, or two of the founders of the analytic theory of automorphic forms. And their L functions. Frobenius we know the Frobenius element, which is important. We know representation theory. First, the finite groups. But then, in the hands of Schur, Weil, Harris-Chandra, this became a grand theory, the theory of representations of reductive complex groups. And those are two of the contributions of Frobenius that are absolutely essential for the modern analytic theory of automorphic forms. And of course, in the case of Hecke, it's the L function that bears names. In other words, all the L functions that I introduced in the letter to Vey or in the lecture 45 years ago were created in order to generalize what I learned from Hecke. And to, of course, connect it to Artin L functions. But Artin was an algebraist, a number theorist. Hecke really, so I think these two people have very special roles for someone who's interested in analysis, in a theory of automorphic forms as a branch, as part at least a branch of analysis and partially as a branch of representation theory. Now, there are two names I would like to add to theirs. One is Siegel. Siegel, there are three, in fact. The works of Siegel really, as I've said elsewhere, rescued the theory of automorphism, the 19th century theory of moduli space of quotients of G by gamma from oblivion. So we owe him a great deal, and I certainly personally owe him a great deal. And I would like to add the name of Maas. Maas was not such a mathematician at the level of these others, but Maas had the one idea, namely which was decisive, to go from the holomorphic forms to general forms. That's his idea. And I think for anyone who's worked so long in the theory of this vector theory of automorphic forms as I have, it's a great gift. Selberg took over Maas's ideas, and he had a technical skill that wasn't available to Maas, and he really extended the analytic theory, did a great deal more with it. And then also he extended the Frobenius reciprocity law, which I didn't mention it here, to a non-compact situation, to a situation of discrete groups. And so we owe Selberg a great deal and Harris-Chandra a great deal. And now, I want to comment on Siegel. I want to comment just briefly on Hecke's collected works. And Frobenius' collected works. So what I'm doing, I'm just filling up the last few minutes. Hecke collected works have a preface by Siegel. And I must say that this preface is condescending. I can't say I like it. As much as I admire Siegel as a mathematician, it's condescending. The collected works by Siegel, by Frobenius, also have a preface by Hecke, who was a student of Frobenius. But it's just a personal reminiscence of Siegel in the class of Hecke, Frobenius. No, he really doesn't discuss Siegel, Frobenius as a mathematician. And as I say, he doesn't, I think, recognize that the contributions of Hecke to the theory of automorphic forms were at least as important as his own, if not more. Now, Frobenius' collected, neither Hecke nor Frobenius' collected works have a real preface. Well, Siegel's a little better here. He does discuss Hecke's works. A real preface. But the editor here for Frobenius just doesn't seem to want to say anything. I don't know why he was asked to be editor. I don't know why he doesn't want to give an appreciation of Frobenius' works. The necessary appreciation is, in my view, not so obvious. I've never seen anyone discuss anywhere the very rapid response of Frobenius to Hecke's questions about the group determinant. So I don't know whether Frobenius is really sufficiently well appreciated by us today. And I think what the editor failed to give, what Siegel certainly failed to give, is some essay which described exactly what Frobenius' accomplishments were and the level at which Frobenius sits or stands or can be placed as a mathematician. So I like very much the idea. As I explained in my notes, in the pages of my website, the introduction of what I call the Hecke-Frobenius conjugacy class is an essential notion, maybe the essential notion, and discovered in the context of Eisenstein's series of the mathematics that I associate with automorphic forms, that some other people associate with automorphic forms. It's just the essential element. It does not appear anywhere, but in my paper, at least at first, in my letter to Vey and the first lecture, the lecture in 1969, and so I feel that I'm entitled, as author of the notion, to provide the name, and I suggest Hecke-Frobenius element. I just wanted to add that for